Hey, good morning, AP Physics. Wanted to review a couple of things as I'm grading your simple harmonic motion labs. I'm learning a couple of things that we need to improve upon and because we don't quite understand quite well, at least not well enough. And then as soon as I've reviewed those things, then we're going to take a little bit of data for the next simple harmonic motion lab, which deals with a simple harmonic oscillator with multiple springs. So let's start right here. This is a review from chapter 6 about Hooke's law and how springs work. So I've made an XY axis here, and on the Y axis, I've got the force needed to compress a spring. And then on the X axis, I've got X, how far that spring is compressed or stretched. So let's just talk about in one direction for a moment. At its natural length, we'd measure X as 0, and then an ideal spring is going to take a linear amount of force to stretch the spring further or to compress the spring further. So if you go out to some distance X, it's going to take a certain amount of force F. And if you go out to a distance 2X, it's going to take a force 2F. Well, this restorative force towards an equilibrium position for a harmonic oscillator has to be linear like that for it to be a simple harmonic oscillator. So when we went through the notes, when we were about a mass on a flat surface attached to a spring, and then that spring is attached to some order, we recognize that the x equals 0 is in fact the natural length of the spring, and that if we're displaced this way or way, if we call one of those directions positive and one of them negative, that the force required is going to be if we displace a distance x, then we're going to have a force back towards the center that is back in the other direction. So displacing distance x, we'd have a force back towards the center of negative f. If we were half, we'd have negative half f. At the equilibrium position, there's no restorative force. If we were displaced to the left here, some negative x, there'd be a force back towards the right. X, we'd have some positive force F, and at 2x, we'd have positive force 2F. So again, we get that linear relationship between force and the displacement. Now, let's talk about that in terms of energy. So remember that work, we always want to go back to our fundamental ideas. Work is force times distance. So if a simple harmonic oscillator is at its equilibrium position, and we do run that system by compressing or stretching the spring to get it going before it starts oscillating on its own, we do work. But FD means the average force through the distance, not the peak force. And since the force changes as we compress the spring, we can't use just the max force. So there's a section on this in chapter 6 if we want to review it, but let's review right here, right now. If we have a max force of 2F, we've displaced it through a distance 2x. Let's call it 2 here. I always want you to think about what the slope of this graph means, what the delta of that graph means, and what the area of that means. The F over x k. Slope is the spring constant. If the spring is different, we would expect this graph to have a steep but still linear line. And if the spring were softer, it would still have a linear graph, but it would be steep. Now, the delta is just the difference between the max force required at the natural length at equilibrium. We reset 0 to the equilibrium position if there's other external in the system that's constant. The area be F times X. Well, that is FD. The issue, however, is that this force isn't average. That force is changing. So since the force goes linearly, if you go out to a certain displacement and you think about the maximum force at that displacement, the average force would be the of all the forces along the way, which is precisely half of max force if you started at 0. So think about the area and all the work done to compress a spring to a certain distance. The average force would have the max force. So if we draw a line at the average force, you can see that this area here would fill in this area here. So the average force along the way is simply the maximum force to compress the spring divided by 2 times x equals the work done to compress the spring. So we do more work in the last half of or compressing a spring, way more work than in the first half, because the force is increasing and the distance is increasing. Interestingly, that's why 1/2 kx squared potential energy of a spring. Let's think about what this would substitute to. Remember that k is F over x. So if we put in 1/2 F max over x times x squared, what we just found is F max over x times x squared. This cancels and that cancels. This turns into F max over 2 times x, precisely what we have for the work to be done to compress the spring. So the work done to compress the spring is proportional to x squared, not to x, because the force is increasing, staying constant as we compress the spring further. Anything that's hooked up to a device like spring that's going to cause a restorative force back to an equilibrium position, that force grows linearly as the displacement from the equilibrium position increases, will build a simple harmonic oscillator. That is the fundamental understanding of how a simple harmonic oscillator works. We include that in our logic when we analyze whether something will oscillate as a simple harmonic oscillator. Now let's talk about multiple spring systems. So let's say we have a multiple spring system. We have a spring with a spring constant A. Its natural length is this long. If we get to mass and force down, we could attach it to, say, 3 of these springs, and it would find some equilibrium position with the springs being stretched a little bit. Let's think about the free body diagram on the mass. If at equilibrium, then that means the acceleration is 0, which means that force is 0. So the downward force must be, and the net force must be 0, so each one of these must be pushing forward force equal to 1/3 g. All right. Now, that would all add up to a net force of 0. Consider if we displaced this below the equilibrium position. So if we displace it below the equilibrium position, then we would have mg is still the force downwards. That hasn't changed. These springs are now stretched even further. Their natural length, remember, is up higher. They're going up further than they would have. But each of them will do that. Now, if we were to add these 3 forces to each other, we could just stack them. And then subtract the weight. We'd have the net force that is upwards. Now, if we displaced this the same distance down again, right? What we see is that the difference between this force and this force is the increase in the upward force. So if we displace this mass from the equilibrium position twice as far as we for the now we'd have a little bit more force from each of the springs, the same force, and we add the other force that was half the distance. So if we make a graph of position negative x, positive x, versus force, net force, remember, because that's what causes the acceleration. At equilibrium position now, not the natural length, is where the net force would be 0. And we displace down a certain negative x, we're going to have a net force upward, so negative x displacement, positive upward force. If we displace twice as far in the negative direction, the force increases to twice as much as before. Now, when we displace it above equilibrium, so let's say the equilibrium position was here, then the upward force in the springs get smaller. This is a little longer than natural length, and so it's still going to be pulling up just a bit. So if we drew a free diagram, it'd be a little bit of force up from each one of the 3 springs, and the same m down. And if we add those together, what we get is a net downward force. If it's displaced the same as much as the original one here, we get the same amount of force that we did displaced below equilibrium as we do when it's displaced above equilibrium, only now it's down. So our displacement is positive, it's up, positive displacement, and a negative force. And if we displaced it even further, then the upward force from the springs would actually become a downward force from the springs because they'd be compressed shorter than their natural length. So at this displacement, our free body diagram turns into some downward force from each of the springs plus the downward force of mg. Add that all together, and we end up with the same net force as we did when it was that far below, only that force is now a negative force because it's down. And look at the graph we made. A linear force growing with x, just like we did for the single spring. So the slope of this is still k, right? The slope of that would be k of the system, not the k of any one of the springs. These springs work together. There's no difference between one stiff spring and 3 less. There's no difference between 3 stiff springs working together, or 3 not stiff springs and 1 stiff spring. They work together. So as long as these are identical, then the spring constant of each of these would just be the k of the system. Okay, so wanted to maybe dove into multiple spring systems to understand those 2 points. If you have a system where there is some side force that is constant, that's going to adjust equilibrium position, but it's not going to change this linear value of how force grows with from that equilibrium position. So that device is still going to act like a simple harmonic oscillator as long as it's not displaced so far, stops the spring from working the way we expect it to. Now, let's connect that to pendulums. When we talk about why a pendulum acts as a simple harmonic oscillator, we got to talk about this restorative force. Again, if that restorative force is proportional to the displacement, then we have a simple harmonic oscillator. So if we draw a free body diagram of a pendulum attached to a thin string, it is, here's our object, it weighs something, and then in that position, the tension, that object, if it's at rest right here, is going to start accelerating back to equilibrium position. The acceleration is going to be back towards that equilibrium position along the path of the circle tangent to it. Then the net force must be that direction also. So if we know there's going to be a net force this way, then we know that the tension must be that big. Now, this angle right there is going to be a right angle because the acceleration is a right angle to the direction because the is tangential to the radius. So this would be this right angle. This is mg. It'd be mg sine theta. So the restorative force is proportional to mg sine theta. Well, of course, graph mg sine theta at 0 to 90 degrees out to 180 degrees, what we're going to get is a sine curve. So at 0 degrees, sine theta is 0. And at 90 degrees, it's going to max out to something. And a sine curve looks something like this. This first is linear. That first part looks just like this. In other words, the force to displace a pendulum, at least through small angles, grows linearly as the angle grows. So we've got this proportion between the restoring force, in this case not being proportional to x, which is actually a distance through an arc, it's actually proportional to theta. So since restorative force is caused by gravity and the fraction of gravity, mg sine theta, actually restores the pendulum back to its equilibrium point at the bottom, grows linearly as angle grows, at least for small angles. That's why it can act like a simple harmonic oscillator. All right, last bit of today, the lab. So let me bring the lab in for you to see so that you can understand what the lab is about today. Since systems here for you here is not just so you can see better. What for is a spring on a flat track with a part. I'll size get the whole thing in the frame all at once, but you'll get rigid one side. It's attached rigidly on the other side, and so we've got a multiple springs position. So the equilibrium position is when two springs are pulling equal amounts of force in opposite directions. You can see this from that equilibrium. This spring is pulling to the left as hard. This right harder. That increases, both of those increase the net force to the right. And so if we release this, you can get simple harmonic oscillator. So you get mass for start. And all this, we can get the period of oscillation with two springs. And I've also already timed it. Add a second spring to this side. When we do that, it shifts the equilibrium. It shifts the equilibrium position. But it still acts as a simple harmonic on the video. Now, the last piece of data, so do that. So this is a piece of zinc. I took class about zinc, and when I put it on top of some and so expected increase. So and we'll have that. All right, let's play that for you so that you can see it. Zoom in on it. So here's the huddle video that I made. And I'll show you how I'm data here. As we put the video, I actually like to use the first pause is on the other side, so I'm not involved. So that turns around right there at 1.86 seconds. Let's notate that. All right. 1.8 seconds. And through, there's half an oscillation. There's one oscillation. There's a second oscillation. That's the third oscillation. So we'll go to the second oscillation. All right, so 1.86 seconds. Starting point right there. Going forward. There's two oscillations. Right there. It looks like it turns around 6.3 seconds for a second oscillation. So zooming out here. Here's the table I made for you, and you might want to take a screenshot of this. This is where the data for lab today is 6.3 seconds minus 1.86 seconds. Grab my calculator here. If we subtract those, two oscillations took 4.44 seconds. It's not the period, but if we divide by the two oscillations, it will be. So each oscillation is 2.22 seconds. So I did a similar analysis with just on a flat springs, and that was damped. So 5 oscillations took 8.76 seconds. I was able to time 5 oscillations. Then I did flat spring. Let me show you the video of that. We have a feel of what that looked like. Here we go. Here's flat spring. So at this 3-speed that I displayed the left now, positions are close to idling. I went far there, and you must see that back. There. That restorative force. And so where I go to bring we're in fact we'll go to here. This is still a little bit of slow. Idea how oscillation works on oscillation. So using on this side, bring on there. This is where I find a start point of first used 5.7 seconds. 0.67 seconds. That is the turn around side, and then 0.37 seconds. That is across here. There's 0.37 seconds where it started around. So that's got this data. And by the way, trying to find the period of a simple harmonic oscillator rather than timing lots of short individual periods, as I saw many of you do in the lab, and then trying to average them. I strongly recommend you simply time over more than one oscillation, count the oscillations, and divide the total time for multiple oscillations by the number of oscillations. You'll get a much more accurate period. So there's the data for today's lab. The number of springs attached to the cart and whether the zinc was on it is here. The track was flat 3. The number of oscillations and the time it took to have that many oscillations is here, and the cart the point 491 is in the corner. Today to review go to work on this lab. That's what due by Friday. Hey, I hope you're having hope you had a good weekend. I hope you get to enjoy some time this week. One of your assignments, if you look at the agenda, is just to find something that makes you healthy and happy and do that for a bit. We got to keep our spirits up. About 3 weeks away from the AP test. Thursday, we're 3 weeks away. So we'll keep reviewing on Thursdays. Thanks for tuning in. Hope you learned a lot about simple harmonic oscillators and the forces and the harmonic oscillators. We'll see you next time.